Hello, everyone. I'm Tim Sonderbroek. I'm from San Diego. I work for General Atomics. I'm a physicist and software developer. And I'm here to present to you Fuse.jl, the power of Julia for the Fusion community. This has been a huge collaborative project with many, many co-authors. So, it's not just me, myself. So what actually is fusion? Let's go with that. So fusion is kind of an energy source. It's very naturally occurring in all throughout the universe. You might know them as stars. They're kind of like big plasma balls, and they're gravitationally confined, and then they kind of generate conditions such that fusion can sustain, and that's kind of like opposing the gravitational force inward. You get a nice balance. These things are pretty large, and they have tremendous amount of energy output. So we want to use the similar concept. We want to also use fusion on Earth to produce electricity. So how do we do that? We cannot use the same method because we just don't have enough stuff here to kind of like confine gravitationally. So we have to use a stronger force, and that's kind of called the magnetic force. The biggest and best contender right now for this concept to work is the tokamak, which is much smaller size, is an order of 10 meters, and we're trying to aim for a net output of like a gigawatt of power. Here you see a cartoon picture of the kind of magnetic structures inside of a tokamak. And in particular, you can see here, let's start with that, those field coils here, they're called the toroidal field coils. Then if you run a current through here, you generate a magnetic field in this direction. That's kind of called the toroidal field. And then you ramp a current through the central solenoid here in the middle. And then through transformer action, you kind of introduce a plasma current in the same direction, which if you know from high school, if you do the right-hand rule, you generate a poloidal field. If you combine those two fields, you get a nice, like a helical kind of shaped field. That's kind of like the black one here that kind of goes around. And it's like winded. And kind of a key thing to take away from this is that you want them to be very winded, because that's kind of, it turns out to be the safest way to operate this. Because if you run at like a low safety factor, is Q here, the plasma will start kinking itself and throwing itself into the wall, and you get a major disruption. So let's focus in a bit on the plasma here. So from the hot fusion core to the cold edge. So here you kind of see the same picture, but now like focusing on the plasma. And you can see that it's kind of a self-organizing magnetic topology of the plasma, where you see this kind of like a cross-section, where in the deep core you have a very hot plasma, and then like when you go outward, it gets cooler and cooler. Because at the edge, it needs to be connected to the wall. Like as you can see, this is a picture of the tokamak, where if you follow the kind of the loss closed flux surface here, you will see it hits the inverter. So it has to be cold on the edge, and it needs to be very hot to kind of generate the fusion power. This is a toroidally symmetric structure. And you can kind of like represent all your quantities in 1D. It's kind of like the rho you'll see like further in the presentation. This rho kind of is the coordinate. Interestingly, if you look at this figure here on the right, you see that fusion power generated in the sun on average is much, much lower in, like if you take a cubic meter, there's a lot less fusion power being generated that we're trying to aim here in the tokamak. And the way that we can kind of achieve that is by going for the most like reactive like fusion cross-section reaction, which is with very light isotopes, namely with deuterium and tritium. Deuterium is like naturally abundant everywhere. Tritium, however, we have to kind of like self-create, and we do that by using the neutrons that we create inside the deep core, like right in here, and that's then gonna like hit the blanket, this kind of like orangey looking structure here. There it will react with lithium and then produce your own lithium. There's some other features here. There's kind of like very close to the super, super hot core. You have things that need to be extremely cool, like the superconductors, like the toroidal field coils. So you need things like heat shields in order to make this happen. So where are we today? There's been many, many tokamaks built and operating all around the world, throughout all continents, but none of them are producing net electricity. So we're here to, let's deliver fusion energy to the grid. And let's now kind of like say where Fuse fits in. So there's a bit of a problem with the traditional concept and design workflows, where there are broad system code analysis to target like individual designs. Expert then run high fidelity analysis on each subsystem, but unfortunately, when you do that, you run into major issues because you have a wide array of like domain experts that can't quite agree and will start to diverge on the concepts. This will also kind of lead to premature design lock-in that kind of limits your exploration in this huge like optimization like space. And many of this then kind of becomes manual integration and kind of this desperate analysis instead of like a cohesive, like holistic view of it. And that's what we're trying to bring. So that's kind of like our goal, to bring a holistic framework. So the needs for this framework is to go from an idea to concept design in minutes rather than months or even years. Evaluate wildly different concepts just along the same footing. Provide different physics and engineering teams a high quality integrated representation of the design. And then you can support the modeling needs all the way from design to when it's running, because there's also like control. And the more you know about your physical system, the easier it is to control. So a quick outline of this talk. I'll quickly go over what we're doing in the framework, and then I'll explain some plasma physics models, engineering, plant, and costing. And then kind of my exciting part is like showing you how we do kind of machine design and kind of large multi-objective optimization, and a little bit of wrap up. So starting with the framework, it's developed from the ground up based on our modeling experience and other frameworks that we've built in the past. It really revolves around build data structure that's kind of like became an international standard, the ITER IMS standard. And this kind of enables like a huge fidelity hierarchy of different models that you can run on the same data structure. And all of this is developed in Julia. So while we support the whole fidelity spectrum, what I mean with that, like there's like first principle codes all the way to like little analytical expressions for specific physical phenomena. So all of it is that is supported, but generally try to balance fidelity with speed. And then we try to use machine learning to get like to almost real-time speed at high fidelity. So we strive for sufficient fidelity to get the interfaces between subsystems about right. So expert in-depth studies should not have to find huge mistakes in the designs. And after that, be as fast as possible. So modeling a fusion power plant is quite complex, as you can kind of see here, because there's not only the tokamak to consider, there's like all these different subsystems. There's things like neutronics, like blankets, like balance of plant and costing. So traditionally it's done by a huge team of experts, taking months up to a year. But we made something that can kind of run automated and do all of these different analyses in together. Kind of that brings to a speed up, if you can run in about a minute, of 500,000 times than what we had before. And that also means that you're just limited by compute and not by man hours. And it will save you a lot of money, of course, if you do it that way. Going over the plasma physics models. So plasma physics models is kind of like bringing all the different physics models together, because there's many different like ways that you can look at the same like at the same plasma. And one of them is kind of like the equilibrium of how it's kind of like defining the geometry. So here you see, for example, some simulation results of how you find those kind of like magnetic field line topology. Then we go like towards like some transport and heating and current drive. That's kind of like briefly said, the plasma does not want to stay very hot. It wants to spew all its like energy and particles out, and that's kind of known as like turbulent transport, while you're trying to heat it at the same time and also have self-heating from fusion, of course. This method is like tightly coupling the transport and the heating together, such that you find a balance between the flux outward and inward, as you can see on the figures on the right, where you have like the total sources in blue, and then like where you have the total transport, which comes from different channels adding up together. Next is you have a current density that, like I was talking about, the plasma current that's going around. that is, of course, also a profile in the same like dimension as row space. And this needs to be updated to get to your next iteration, because the way that this works is that all of these different pictures are coupled together because they all are depending on each other. For example, you cannot really do transport without the geometry, and you cannot do the equilibrium without having like some current density profiles. So you run this many times, and then at some point you kind of reach self-consistency and convergence. So does any of this work? You know, it sounds nice that you can do this very fast, but does any of this work? So let's compare fused plasma models with experiments. So here on the right, you see kind of like a plasma shot, the temperature profiles of a plasma shot being locally run at General Atomics in San Diego. And you see the experimental results, like with error bars in blue, and then the matching results from fused in orange, showing a pretty good agreement for this kind of complicated system. So that's just one single tokamak. We've also done large multi-machine database studies. We have the tokamaks that I've kind of described earlier from all over the world, from the small ones like Compass and TCV, all the way to the ones, the ones in the UK like JET. And you see a very good agreement between the predicted energy confinement time, which is kind of like a global like metric of how well your confinement was, against the experimentally recorded ones. So this gives us kind of good, confidence that our models are working as intended. So next up is very important other stuff, is kind of like the engineering and the engineering aspect. Because plasma physics is fun, but it's not the primary component actually. So we're able to do automated tokamak builds, where we go kind of from 1D radial, where we kind of base requirements on like very technical like stress limits and things like maintenance and neutronics, to 2D cross-section, where you're introducing things like diverters that have to take up the heat load. And then we can all the way go to 3D CAD via GMesh. So, and then you can use mesh generation. And then, as an engineer, you can take this and do any of your heart's desire if you finite element analysis on these kind of like end result designs. So another thing to talk about is kind of the superconductors. Superconductors have a certain critical current density that they can run it. So how much current you can pump through a loop, to a wire. And they're kind of limited by an external magnetic field. So you kind of, there's different types of superconductors. There is the low temperature superconductors that we have already built, like the ITER ones. And then there's the high temperature superconductors that the field is actively working towards. So here you can kind of see that the ones that we currently have, the green ones, they're kind of sitting at the low end of the spectrum, and that these new blue and like orange one kind of like expand this phase. Another kind of thing that you have to consider is I talked a little bit about the TF coil, like a magnetic field, and the ohmic solenoid, the central solenoid one. But you also have to kind of like shape the plasma. As you see here, the boundary needs to be along this surface here. And the way that you do that is by kind of optimizing the poloidal field coils. So these are like coils going all the way around like this, which you can set at certain currents, and then that will pushes or pull the plasma into this particular configuration. So you're trying to do an optimization along this rail, such that you have your control points around here are matching to your plasma shape, as well as your target needs to be right at this diverter where it can take up the most heat load. And here's a showcase that even if you flip like kind of the plasma shape, the build and everything, and the poloidal field coil optimization works just as intended. So next up is neutronics. Neutronics is another important thing, because I briefly mentioned we need to make our own fuel. So there's a huge amount of like neutrons being generated right in the core, and then they're shooting in every which way. So you kind of have to do, you have to count up where they're hitting and how much tritium you're producing. Yeah. Another thing is, we're creating 1 gigawatt of power inside of this like rather small area, and it needs to go somewhere. So this is kind of another challenge that we have in tokamaks, is that we have a lot of heat, the plasma touching the diverter. So here you see kind of like the flux hitting the diverter regions, and then you have like the neutrons being generated and hitting the first wall here, as well as kind of radiative emission from the plasma itself. So this is a way that you can kind of design your first wall such that you're below the amount of megawatts per square meter that your material can withstand. Last but not least, we're also looking at the kind of like sophisticated advance of plant models that provide kind of realistic thermal conversion cycles. So remember, I showed you just the 3 kind of like main points where the energy kind of comes out, and if you put those 3 kind of like this in the loop, you have kind of 2 main cycles that you can transform your energy from thermal to electrical power. That's either the regenerative Brayton cycle or the Feedwater-Rankine cycle. The Julia has been quite great for this because we can use modeling toolkit here, as it's a nice little like graph that you can connect, and it's validated against like thermal flow, which is kind of like a state-of-the-art like thermal engineering tool. Another thing that is we should consider if we want to make this commercially viable is the cost of all of these like components, because who wants to build a machine that's too expensive? Because nobody's going to pay like $10 for a kilowatt hour. So we're synthesized like 2 different like models in literature and kind of updated them to like present day, inflation and like new technologies like high temperature superconductors. And this will be very useful for when we're doing machine design, which I'll go over right now. So Fuse is, because of the speed, it's kind of the first tool in which, for Fusion at least, where you can use kind of like multi-objective constraint optimization workflows to explore a very large design space. And the best kind of tool, like shout out to MetaHeuristics, is a genetic algorithm where you find solutions that then steer towards your Pareto front. So for example, here you have a 2-dimensional multi-objective optimization. On the one hand, you want to minimize capital costs, and on the other hand, you want to increase this was the safety factor from before. You want to make this as large as possible. So the genetic algorithm will then kind of push your front to and create a population of which they're Pareto optimal, because the reactors here right at this point are the cheapest, but they're not as safe, while they're here are very safe but very expensive. And then you have things like investors and policymakers who can kind of like figure out how much they would want to invest in terms of this safety factor. It's incredibly scalable, where we can use like HPC systems because it's super parallelizable. We can run like 100,000 cases in a few hours on a small cluster. And this is also kind of a formidable stress test of your tool, because you're running the entire design space, to do this kind of like, you find the most number of bugs in the craziest way possible. So here is kind of like a design study, or where I'm trying to compare kind of like 2 different like plasma shapes. This is kind of like all the rage in tokamak like physics right now, where you flipping the triangularity. So here you have a normal shape, or like this, and here you're flipping it, which has very different properties. But we're not quite sure whether or not it would actually be able to be viable in terms of like, it has a lot of good properties, but we're not sure if it would be viable for the confinement metrics. So this is kind of what the optimizer is doing. This is a 2D histogram. So where the x-axis is kind of like the generations in time. So initially it's fully randomized, like in this actuator space, and you'll see that it's unable to produce net electricity. One of the constraints that it needs to go towards is that it needs to produce at least 200 megawatts electricity. So after some generation, it finds how to do that, as well as the other constraints. Then you can see that the optimizer is once it finds like a viable population, then it really like pushes it down towards like minimizing the capital cost. And lastly, you kind of have this 2D trade-off again, like against capital cost against safety. And you can see that in color here, you can see that the cheaper ones are smaller and at lower field compared to the more expensive ones. So basically, this is kind of indicating that you can buy plasma safety with larger and higher magnetic fields. Here is the red one is kind of the negative triangularity one. So it sits far above the positive triangularity one, which means that it's more expensive as we kind of expected compared to the positive triangularity one. But there's other considerations, like, I mean, I won't go into detail because it's quite complicated, but that need to be considered in order to count them out. And so a kind of like a risk factor kind of idea would be another wonderful axis to put on this to kind of capture these other effects. So here I'm showing kind of a new technology versus like a very robust one. I was talking about the different superconductors. So right now we have working like low temperature superconductor, which are the dashed lines here. So you see that this space is rather small compared to getting to new technology. So this kind of tool is also kind of a way to see what kind of technology developments would bring what benefits. And then let's go over the wrap up. So we're open sourcing Fuse to the community, as it will be a powerful platform for integrated simulations. We already have IMS GD.jl open, which is kind of like the data structure under the Apache 2.0 license. But the rest of Fuse will be open soon. And this is like 25 packages with at least 200,000 lines of code. And here you see a nice little like word map of like all the packages that we have. So what's been our experience with Julia? The pros and cons and kind of our perspective. So we really enjoyed like writing code in Julia, as it's very high level like Python. It's fast to see, but you have to definitely put some effort in to kind of reduce your allocations and do profiling. But once you do that, it's very, very performative, just like Fortran, because most of our code base is in Fortran, so we're kind of like porting and rewriting everything. And that experience also has been very insightful. There's a lot of time saving. Like the last presentation kind of went over Documenter. Like you don't have to do that much extra in documentation compared to like older codes. Cluster integration is easy. You just like install you download your package, and then you're almost ready to go as from the get-go. We are using Makefiles to manage our 25 packages, but when we're working towards like properly like releasing them, then we will use a registry and like use proper version control. There's been sizable improvement to Julia as we experienced over the years. And it's been actually pretty reasonably stable for, depending on at least 600 dependency in our code base. We've been trying to use auto differentiation, but it's hard to keep everything like auto differentiable. But that will be the goal. Some colleagues that are working on kind of like the like large HPC problems that run like months and months on clusters. They've also been trying to use Julia. They've had some difficulties, like coming from like Fortran and being really expert in MPI and all that stuff, to resolve the type instabilities that kind of come up. And it also looks like the Julia build system is not quite ideal for HPC users, as they're quite limited to, they don't have as much control over the cluster environment with specific hardware drivers and such things like that. So a little shout out to Julia Hub, to Steve Kelly and Michael Volagna, who helped us with some speed ups to reduce some import time and code execution, compile as an executable, and working a little bit on memory management using distributed. To conclude, Fuse is a major leap forward in the whole facility modeling capabilities for the Fusion community, and we love to bring many of our people to Julia, and it will be great because right now we're using kind of a Python framework that is, yeah, it's a Python framework. There's always more to do. In the near terms, we're applying like uncertainty qualification and risk, and we're always on the scout for better and reduced models. So this was my presentation, and thanks for listening. Are there any questions?
Thank you very much for this presentation. I think it was the most complete presentation I ever saw regarding fusion energy. And I did my PhD on a floor at the TUE where they were also doing fusion research. So that was very, very complete. Do we have any question? One there.
I was curious about the motivations for moving things from Fortran to Julia. Like, could you have left some things where they were, or was the big benefits you were gaining by porting them?
So the biggest thing is kind of having like a clean slate, like to really develop from scratch, and especially when because we're mostly coming with like plasma physics models, right? Like really highly computational like things. But when you're developing something new, it's very nice to use Julia. So it's mostly, yeah, like kind of like porting some packages, and then you have it all in one system, so you don't have the multi-language problem anymore. That's kind of like the design philosophy. So everything is tightly coupled instead of like a file-based system.
Thank you.
I do have a question also. So when you convert your code from, for instance, Fortran to Julia, do you think large language models can help you with that?
Oh, we're absolutely using them all the time. We had actually like a bachelor student who came and worked with us, and he was able to port like a huge Fortran code into Julia. Now we have our own Julia version of that, and he was able to, yeah, it was quite amazing.
Yes, I was just wondering about the physics models of the plasma, because I also did a PhD in plasma physics many years ago, and I remember they were very tricky. You know, plasma modeling was not easy. I guess the Fortran codes had developed quite a lot, but were you able to leverage some things in the Julia ecosystem to make it easier to implement re-implement these models, or was it a case of really you had to redo the code from scratch?
So there, you know, you learn a lot from the codes in the past, right? So you already have a really huge understanding of where you're trying to go. And on top of that, there's also been a lot of reduced models made by the community. For example, when we're talking about turbulence here, there are huge supercomputer like, you know, models, but there's been kind of like, you know, understanding of what's actually driving the transport, such that those are things much easier to implement.
Okay. Thanks.
Thank you. Any other question?
So you have multiple submodels. Do you validate them separately?
Yes, I mean, yes. So we take them also out of literature, and like you say, you validate them on the tokamaks that are already running. But not everything you can, of course, validate, because we don't have tokamaks that are producing net electricity, right?
So what do you do then? You need to validate it somehow, because you based very important and expensive decisions based on the output.
That is correct. So part of it is you running it on an existing like kind of like data set, right? Like that we have on all these tokamaks. That kind of, and if you're using the same exact model for all of them, you have kind of like a confidence in extrapolating. The inverse of that would be using kind of like really hacky system codes that are kind of this linear regression on data sets. And so will always be a step up from using linear regression, which is kind of used in the tokamak community right now. So you can, of course, not like validate your models on a thing that doesn't exist, but this is the best we can do.
Okay.
A question here.
You showed this cost estimation. How's this done?
So that's a good question. Costing is definitely a really tricky one. So there's things like material costs. You just need a certain amount of like lithium, right? That has a unit cost, and you can kind of keep track of that in industrial costs. And then you have components like external heating, like gyrotrons. that are very used everywhere by the fusion community around. So you also have a good estimate for those. The tricky ones are the ones that are like the expensive superconductors, right? Those are not fully fabricated with large scale, so you kind of have to indeed like make some estimates based on like past, extrapolate outward and kind of like estimate it. So although the absolute number of the costs might not be super correct, what is really important is that you get the relative cost when you're doing these design studies, because that will always be true. Like if you're using less material, it will be cheaper.